Well, welcome back, folks. Daily and Bio here with another exciting physics video for you guys today. Our focus is going to be on position time graphs for acceleration and free fall. So what you'll notice is I actually have not changed the student learning objectives from the previous video. Reason being is that it really is more of an extension of what you learned last time. We're just going to look at applying the information in a little bit different ways. So let's think about some position time graphs of accelerated motion. These graphs would not be linear if the acceleration was increasing or decreasing. Remember that when we look at position and uniform motion, we see that high velocity, you have a straight line. Even with some velocity, you have a straight line. And if there's no velocity, you also have a straight line. But with non-uniform motion, that means that acceleration is changing. And so if acceleration is changing, then velocity is either increasing or decreasing at a non-constant rate. So as velocity increases, the amount of ground covered increases. So if we look at constant acceleration, it actually produces a parabolic shaped position time graph because as you accelerate, your velocity increases, which means you cover more ground as a result. So with uniform motion, meaning that the velocity is the same versus the position, you're going to have linear lines. But if we have non-uniform motion, meaning that the acceleration is changing, that means that the velocity changes, which means that the ground that is covered either increases or decreases. So as a result, non-uniform motion, meaning that there is some acceleration or deceleration, results in parabolas or curved lines in their position versus velocity graphs. The sign of the acceleration determines whether the parabola has an upward or downward curvature. The greater the curve of the parabola, the greater the magnitude of the acceleration. So if you have a very large curve upward, that means that the acceleration is occurring very rapidly and you have a large value for A. So let's rank these curves in order of initial position from most negative to most positive. Well, the most negative position would be the line that starts furthest down on the graph. So that would be A, followed by D, then C, and then B, based on the positions of where they're located on the y-axis. Basically where the line intercepts the axis. Rank the curves in order of initial velocity from most negative to most positive. Well, the initial velocity, the highest is going to be A because we have an upwards line. The line is pointing up. B would then have the next most. You have a constant velocity associated with B, then C, and then D. If we rank them in terms of order of acceleration from most negative to most positive, the most negative acceleration there is D because it has a great curvature going downward. Following that would be C, then B with zero acceleration, and then A with very rapid acceleration moving up. A speeder travels at 18.2 meters per second. The instant the speeder passes a parked police car, the police begin their pursuit. The speeder maintains a constant velocity, and the police car has a constant acceleration of 4.50 meters per second. Show that the police car catches up with the speeder after 8.09 seconds and determine the location where this occurs. So we've got quite a bit of information here that we need to break down. So what I'm going to do is I'm going to make a nice little chart here and just look at the information we know about the speeder and the police car. So the speeder is traveling at 18.2 meters per second. So that's our velocity. The instant the speeder passes a parked car, the police begin their pursuit. So as both things are happening simultaneously, our initial position is 0. The speeder maintains the constant velocity. Well, if it has a constant velocity, the acceleration is 0. We have times of 8.09 seconds for both. And the police car has an acceleration of 4.50 meters per second squared. The question says determine the location where this occurs. So we want to know our final position. Now, here's the key thing. Remember we talked about this in the little supplement video that I added. We need to look at what is missing. And what's missing here, there is no V2 for either of these. Okay. Obviously the initial velocity for the police car is also going to be 0 because it's at a stopped position. Once the speeder passes the parked car, the police begin their pursuit. So that indicates that the policeman is at rest, so V1 is going to be 0. We're missing V2. So if I look at the little chart that was provided, if we're missing V2, we're going to be using the equation x final equals V1 times t plus 1/2 a t squared. So we just need to plug the variables in for the speeder, and the policeman, and then we should get the same value for the final position and where this occurs. So let's start with the speeder. We have our final equals V1, so that's 18.2 times time, so 8.09, plus 1/2 a, which is 0, t squared, so that actually works out quite nicely, because if that's 0, we can completely eliminate that part of the equation and solve for the position. So for this value, we get 147 meters. Let's check and make sure that the policeman did the same. So x of f. So his initial velocity is 0, 8.09 seconds, plus 1/2. His acceleration, 4.3. Acceleration, 4.5. And then t squared, I'm going to cut into that a little bit, sorry, 8.09 squared. Well, this value is going to be 0, so we just now plug in and solve, and we get the exact same value. So I think the key thing here is recognizing the variable that is missing. I can't stress looking at that enough. It really helps you figure out what equation to start with and then what to plug in and what to be able to solve. All right, let's move on. Free-falling objects have constant acceleration. Galileo Galilei dropped objects from the Leaning Tower of Pisa and determined that if the effects of air resistance could be neglected, then all objects in free fall would have the same constant acceleration. The effects of air resistance are quite easy to observe. Imagine you're taking a crumpled up piece of paper from the top of the building and dropping it next to a just normal sheet of paper. Now, in this instance, the normal sheet of paper is going to have greater air resistance because it has a larger surface area, which means that air is going to act upon it more than if it were crumbled up. So we do use free fall acceleration calculations. We tend to not look at wind resistance or air resistance as something we can use, but obviously it would need to be taken into consideration if we were trying to get a more accurate value for something. Free fall doesn't always mean objects move downward. We can move objects upward as well. Acceleration due to gravity is always noted as g, and the acceleration is always 9.81 meters per second squared. So if we drop a ball off a building, not taking into account air resistance, after 1 second, the ball would be the ball would be moving at a velocity of 9.8 meters per second. After 2 seconds, 19.6. After 3 seconds, 29.4. The acceleration is increasing the velocity. With gravity, it's always 9.81 meters per second squared. A boy steps off the end of a 3-meter high diving board and drops to the water below. How much time does it take for him to reach the water? What is the boy's speed on entering the water? So let's do a little bit of variable identification. Boy steps off the end, so his initial velocity, v1, is going to be 0 meters per second. We have a distance traveled of 3 meters. And because he is dropping, you have to imagine he's on the diving board here. Little Jimmy. Splash. Oh, I'm sleepy. The acceleration is going to be due to gravity. So the acceleration is going to be 9.8 meters per second squared. And the question is asking for time. So again, we need to look at our chart and figure out what variable is not included in the problem. In this case, we do not have v2. That is not included. So we're going to use the equation x equals v1 times t plus 1/2 at squared. And since we're looking for t, we're just going to plug in our information and solve. So we go 3 meters. v1 is 0 times unknown t, so that'll cancel, which will be nice. We have 1/2 9.8 t squared. So we get 3 equals half of 9.8, 4.9 t squared. And then we're just going to solve for the value for t. T is equal to 0.782 seconds. Now the question wants to know, what is the boy's speed on entering the water? So what we're solving for is v2. So we can pick pretty much any equation that we have where we have a value for v2 and solve. So let's just use that very first equation. v2 equals v1 plus a times t. v2 equals 0 plus acceleration due to gravity times time, 0.782. What we get is v2 is 7.67 meters per second. Okay. So again, the only concept here is free-falling objects. Your acceleration is going to be 9.8 meters per second squared. The rest of it is just based off of the stuff that we've done last time. Again, key thing, figure out what variable you do not have, because that is key in figuring out which equation we're going to start with, and then you can move forward with the rest of the problem. So again, just more concepts directly related to the 5 equations of motion that we've been focusing on. We just focused a little bit more on acceleration and trying to understand the concept of acceleration due to gravity. So hopefully you got a lot out of this video. As always, if you have questions, let me know. Again, JLand Bio, make sure you like, comment, subscribe, shop that merch, and we will talk to you guys soon. Have a great day, guys. Bye-bye.